Hello, I'm John Beck. I'm a program manager for the Azure Compute team. I'm here today to talk to you about selecting the right VM size. So, as you're aware, Azure has many services as part of its platform and its infrastructure. And we don't have enough time today to go over all of those, so we're only going to target a few of those. Specifically, the Linux VMs, the Windows VMs, the storages for those VMs, that includes the blob as well as the premium storage, which we'll talk about. And then a little bit about the portal, about how you would actually be able to create a VM, be able to manage a VM, upgrade a VM, and as well as delete a VM on the system. Before we jump into jumping into the VMs themselves, I wanted to talk a little bit about, it's important to know where you want to put it. And as you can see by this slide, we have over 28 different regions available to you today. Some of these are not quite launched yet, but 22 of them are. So no matter what, if you wanted to release it inside of US West or US East, or maybe you wanted to put it in Japan or in China, we have a data center that will support you. Of those 22 regions, or 28 with all of them, there are over 100 different data centers to support that. So that's an important piece of deciding what VMs you want, because not every VM is available in each of those regions, but for most of them they are. All right, so one of the important questions we get asked a lot is, what VM size is right for me? So that's why we're deciding, you know what, let's just introduce people to the different VMs, and that'll help them, inform them on what VM they should be selecting for the workload they're doing. And the important part there is, what is your workload? Because not every single VM is going to work for every single workload. So knowing which workload is important. And we support several different workloads out there. Common ones that we see is the dev and the test scenarios. So the companies don't want to have to buy a bunch of on-prem hardware just to be able to do dev test for 8 hours of the day or 12 hours of the day. Instead, they can come to Azure and they can spin them up as they need them and put hundreds and hundreds of cores in there, or even thousands of cores. And then at the end of the day, they can shut them down and not be paying for that expense overnight. So that's important. Then there's also high performance computing. You'll hear a little bit about that later. Enterprise applications like Exchange servers and SQL and MySQL and Oracle and all these different types of enterprise applications. And then large scale data, so Hadoop and other big data providers, as well as GPU intensive, so visualizations and modeling and things like that. So these are some of the workloads that we're constantly building VMs to better support those workloads. So we originally started with the A series of VMs, and we call them VM families. The A series, when it was launched, was expected to be the only series that we were going to have, and we were just going to keep going A through whatever. We've since then changed and had the families. So there's going to be two sets of A's that we're going to talk about today. There's going to be the low mem and the high mem, as well as a HPC. And for my portion of the presentation, I'm only going to talk about that first set, the low mem and the high mem, and then we'll leave the HPC for later. Another thing before we jump right into the A series is, to be able to distinguish between each family of VMs, we needed to create some common measurement. So we created the Azure Compute Unit, the ACU, and that allows us to sit there and say, hey, from an A1, which was the original, to a new G5, what is the difference in compute power between these two? So when we jump into the A family, which is right here, so when we jump into the A family, which we're going to do, you'll see that the A0 or A1 being the first VM, the first VM with the first core series, actually is a 100. So everything will be based off of 100. And the only thing that is less than a 100 is our A0, not the A1, but the A0, which is an over-provisioned CPU. It's a very, very inexpensive VM. So if you're looking for a quick VM to get up in place and don't need very much power or memory, it's the perfect one for you. It's 0.25 CPU, as well as 0.75 gigs of RAM. Then, as I mentioned, we have two different versions of the A0 through A4, and then A5 through A7. The A0 through A4 are actually the low memory, and there are 1.75 gigs of RAM to every core. And I should make a note, unlike all the other cloud providers that are out there, today all of our vCPUs are truly at the core level, not at the hyper-threaded level. So when I say vCPU or core, I'm literally talking about the actual core on the processor. In that A0384, we have two flavors of the A0. 384, and that is the basic as well as the standard. And the only difference between the basic and the standard is the basic has no load balancing or auto scale functionality, where you would normally see that in the standard. In fact, all of the other VMs that we're going to talk about have that capability. This standard come in at, as you can see there, 60 cents per 1,000 ACU, and that trend I'll keep going through the other versions so you can understand the differences in the price per ACU, or at least per 1,000 ACU, as well as the units themselves. People who use this A0 are usually the people who are looking for a low-cost solution. It doesn't need a lot of compute, doesn't need a lot of memory, so that's perfect for them. The people who need a little bit more memory for a heavier compute, heavier access to that RAM, will choose the A5 through the A7, and that's $1.10 per 1,000 ACU. All right, let's jump into the next family, which is our D series. In 2014, we announced the D series, and the biggest difference with the D series compared to the A series is we introduced on the Sandy Bridge, Intel Sandy Bridge CPU. So we see a huge performance gain, which you'll see here. The D series included, with that Sandy Bridge, 160 ACUs per core, which is a 60% increase over our A family. So it's a lot of speed. On top of that, we added a couple more things. We added the ability to have more RAM and more CPU per VM, as well as we introduced SSD to our VMs. And as you can see here, the SSD can go up to 800 gigabytes per VM, or at least for the largest VM, as well as it's 3,000 IOPS on that, and it can do 48 megabytes per second on read, 24 megabytes per second on write. So it's extremely fast with minimal millisecond latency. Another important thing that has been asked for us on these as well, there are two different versions. There's the standard memory as well as the high memory version. The standard memory is 3.5 gigabytes to every core, versus the high memory version is also that 7 gigs. So instead of the 1 3/4 that we were doing in A, we're now doing 3.5 as a default in our D series family. So it's 42 cents for that standard memory, 55 cents for the high memory. All right, let's jump on to the next generation of hardware, which ended up being put on top of Haswell, the Intel Haswell chipset. And it increased the speed and the amount of cores that we have in there. So we called it a D series version 2, so DV2. And the DV2, we're giving you the exact same SKUs again. So we have the low memory, we have the high memory, we have the same SSD drives all the way down there. But because we can actually have more cores and more memory, we have a larger size that we're announcing at Build this year, which is the D15 V2, and it gives you 20 cores and 140 gigabytes of RAM. And again, like the D14 was on version 1, the D15 V2 is that full node. So if you want the comfort of knowing that you're the only tenant on that node, you'll want to get the D15 V2. It also comes with a full terabyte of SSD speed, so it's much more storage. The D series and the DV2 series also offer with the SSD, if you find that it's not enough SSD for you, that you will want to probably get premium storage. So we offer that, and those are the DS series. So there's a DS already available today, and we are just now releasing DS V2. The difference between the specs on those, between the D1 through the D15, or DV2 or D1 V2 through the D15 V2, is the amount of SSD drive you have available. We take a good portion of that, which is ephemeral disk to you, so it's temporary. We take it and use it as a cache for the premium storage, but that is available to you. For the standard memory on this one, again, that's the 3.5 gigs to 1 core. you're seeing 30 cents per 1,000 ACU. So you can see we've come down quite a bit. We started at 60 cents, we went to around the 40 cents, and now we're at 30 cents for that standard. And then for the high memory, we're down to 40 cents. So as we're getting through our generations, that 1,000 ACU is becoming more and more cost effective. So if, for whatever particular reason, 7 gigs is not enough per CPU, and you need even more for big, heavy compute or heavy enterprise applications, we offer the G Series. The G Series is also built off of Haswell. We released it last build, so if you were a build, you saw it there, and it won't be anything new. But if you're new to this, you're going to see that this is the largest VM that you can get on the public cloud today. It actually has up to 448 gigabytes, is the biggest VM with 32 cores instead of the 16 that we were seeing, or the 20 on the D15. So you have a much bigger one, and we have it as low as a 2-core with 28. So we're doing a 14 gigabytes of RAM to 1 core. So it's much bigger. Great for applications, enterprise applications, anything that need fast disk. I didn't mention this, but the SSD on the G Series compared to the D in the DV2 is much bigger. So on that large G5 that I mentioned, you can have up to 6 terabytes of SSD drive. And again, with these G Series, you can actually have a GS, which gives you that up to 64 terabytes. And I'll talk about that next. Because the G Series is bigger hardware, more memory, faster disks, more disks, the price per 1,000 ACU is $1.53. So it's a workhorse. And if you're needing that for large SQL jobs, for Dynamics AX implementations, or Microsoft Exchange implementations, or huge MySQL databases, big data, any of these types of workloads, this is a perfect SKU for you, and it's been very popular so far. All right, so I mentioned it a few times. We have the notion of premium storage versus the blob storage that is so common today. This is the very fast SSD-based storage in the cloud. You can have on one VM alone, whether it be the D or the G, you can actually have up to 64 terabytes of SSD space storage per VM. You can also have up to 80,000 IOPS. That's 5,000 IOPS per disk that you attach to your VM. And with no cache, you're actually seeing around a 5 millisecond latency for both your read and write. And with cache, it's less than 1 millisecond for read latency, which is ridiculous in speed. All right, so I ran you through the A series, the D series with the DS, the DV2 with the DSV2, the G series with the GS. What we're going to talk about next is going to be the high performance compute, which is going to be the GPU and that A series high performance computing. And for that, I've asked Karan to come in and speak from the high performance compute team, Big Compute. Thank you very much for your time.
Hi guys, my name's Karan, and I'm part of the Big Compute team as a program manager. Today I'm going to be talking about the GPU and the HPC SKU VMs that are in Azure today. Firstly, to kick off, the GPU VMs in Azure, Scott Guthrie announced these late last year, and these are going to be a very important VM size for us from a perspective of completing the picture in a HPC in the cloud standpoint. We're going to be coming out with 2 distinct VM sizes, or 2 distinct VMs with 2 distinct GPUs, both compute and visualization. And so we're hoping to solve, the compute scenarios where people are doing simulation, deep learning, neural net, those kinds of scenarios. And then with the visualization, we're trying to solve the accelerated desktop application, so where you're able to run things such as Autodesk Maya, Adobe Premiere Pro, and some other engineering applications as well. You're able to run, simulations on the compute VM, and then you're able to then visualize potentially in the visualization GPU as well. We're going to be supporting all sorts of tools and libraries that are existing today, so you should just be able to literally lift and shift these tools and libraries straight onto these VMs from your on-prem hardware straight into the cloud. So we will support from a visualization standpoint OpenGL and DirectX accelerated applications. We will, from a compute standpoint, support OpenGL and OpenCL and CUDA applications as well. So applications that are built using CUDA language and utilize some of the CUDA libraries like cuRAND and some of the others will be able to run and utilize these GPUs. So one important point about these GPUs is the way we're bringing up into a VM. So we're not virtualizing these GPUs today, or we're not virtualizing the functions of these GPUs today, but essentially we're going to be using a capability called DDA, Discrete Device Assignment. This is part of our Hyper-V suite inside Windows Server 2016, where essentially we're going to be doing a hardware pass-through for a PCIe device. So you will essentially get the entire GPU device pop up as an additional device in your VM. So you'll be able to utilize the entire GPU. Depending on the size of the VM you pick, you might additionally get more GPUs as well. So to go through the list, we will have the K80 NVIDIA K80 GPU from a compute standpoint, which is a very high. It's sort of their best of the breed GPUs for compute, for deep neural net and simulations, and then we will have the NVIDIA M60 for the virtualized visualization compute. Based off of these two different cards, we will have different VM sizes depending on the cores you might need, the memory, and the hard drive size. So depending on the VM size, you might get a single GPU, 2 GPUs, or 4 GPUs per VM. Additionally, on the compute side, a lot of people will be running a lot of algorithms require low latency connection between the hardware, and so for that we will be using or providing RDMA, low latency RDMA between those VMs. So moving on, I'm going to just show you a quick demo of what a M60 VM looks like and potentially run some applications on there as well. So here we have a GPU M60 VM, and if I go into the device manager here, you'll be able to see that within my display drivers, I have a NVIDIA Tesla M60 GPU available to use. So to show off some capability here, what I'm going to do is I'm going to start up LS Prepost, which is an application that's used today for viewing simulations for example, car crashes. So here we have an application called LS Prepost, which utilizes OpenGL technology to visualize, and this is running in a VM today, showing off the capability of the GPU. So you can see the latency is very, very smooth. The lag is almost non-existent here. I can even run a simulation of the car crash here, which is showing off the capability of the GPU. I can move it around. And if you are running existing tools to capture performance data, you'll be able to see that the GPU is being utilized here. So that was a small taste of what a M60 GPU looks like and what an application running on that VM looks like. You should just be able to launch the VM and essentially install your applications and be able to run them seamlessly. Moving on to the other set of sizes that we currently offer in Azure is the A series. So these are the HPC specific VM sizes that we offer today. A8 all the way through to A11. And so the main purpose of these VMs is to run applications that are embarrassingly parallel, require a lot of RAM, a lot of cores, so things such as CFD simulation, also rendering, and also things such as media transcoding. So we have the A8s and the A9s, which are two separate VM sizes. each with 8 cores or 16 cores respectively. The special thing about these VMs is that they also do come with the RDMA capability underneath the covers. In fact, they come with InfiniBand, which is super low latency between the VMs. So if you have an MPI application, or if you have things such as reservoir modeling or simulation that you need to run with a head node and multiple child nodes, these are the VMs that can these are the VMs that you will be able to take advantage of for those workloads. Additionally, we have the same VM but without the RDMA capability. So in case you need the same VM and the power of those CPUs, but you don't need the low latency connection between the VMs, you can utilize the A10s and the A11s. And so we talk a lot about big compute, and we mentioned that not just for the GPU, but we also mentioned that for the HPC hardware that we're currently offering. And the important thing to sort of understand about big computers is essentially batch-like applications and simulations. So it contains things such as running a simple executable, but you might want to run it multiple times on different VMs. So we're talking about things like modeling, analysis, stress analysis, reservoir simulation is one that I mentioned earlier. Things such as transcoding on a very large scale. So if you're transcoding video or audio, another very popular use case here is rendering. So if you're rendering high quality images or high quality animation, 3D animation, you might want to render a single frame on a single VM, and you might want to scale out to thousands of cores. And so the GPU SKU and both the HPC SKU will help you do that. So as I mentioned earlier, there's two types of HPC workloads that we define under the big compute umbrella, and those are embarrassingly parallel. So things such as rendering, for example, are embarrassingly parallel. So if you're running a second of animation and you're rendering that animation, you might have 30 frames that are individual frames or pieces of work that you might need to get done. And so those pieces of work can be done on individual VMs without having to rely upon the next set of work. And that's what we call embarrassingly parallel, where you have a job and you have an individual set of tasks that are independent or orthogonal to each other. The other scenario we have here is tightly coupled, where you might be doing some work or simulation that requires perhaps some pre-processing or perhaps requires MPI applications to run, or if you're doing things such as deep neural net training, where results of one task actually need to talk to another task, and you might need those results to talk to each other, and you might be combining those results into something else. So for that purpose, we call them tightly coupled, where you'd have a cluster of machines with potentially a head node and a set of child nodes, which you can scale up and down as well. So thank you for your time today, and I hope this was helpful from a perspective of giving you an idea of the new sizes that we're coming up at with GPU, and then the existing sizes on HPC side. Hope you guys have a great week at Build, and happy coding.